Hello everyone. Today we are going to talk about minimization problems. First, let me remind you of how minimization works in a problem you have probably seen before. I am quickly going to review a fencing problem. Find the smallest perimeter of a rectangular fence that has an area of 100 square feet. So, how would we begin this problem? Let's first draw a picture to get a visual sense of what the fence would look like. So, we know that this rectangle we are constructing has an area of 100 square feet, which is right in here. But we need to find the smallest amount of fencing it takes to enclose the 100 square feet of grass on the inside. So, we need to construct two sides of length x and two of length y. We can now write the equation of the perimeter from our picture. I'm going to use the notation p of xy to denote perimeter, so we have 2x plus 2y for the lengths of the sides, and we know area is 100 square feet, so I can write 100 equals, remember area is x times y. We want to minimize the perimeter of this problem. We called that equation our objective function. We are using area to help us figure out the perimeter, so we call the area equation our constraint equation. We need to use these two equations to work towards our goal. First, we solve for our x in our constraint equation, so we'll now get 100 over y equals x. Now we're going to use substitution to put this x into the perimeter equation, so we get 2 times 100 over y plus 2y equals now p of y. Now that we have our p of y function, we need to take the derivative. You might remember from calculus class that taking a derivative of a function will find you either a min or a max. So taking the derivative of this function will get us negative 200 over y squared plus 2 equals 0. We can now use this information to solve for y. So let's begin solving for y by bringing negative 200 over y squared to the other side. So we now write 2 equals 200 over y squared. Now let's bring y squared to the other side to get y squared times 2 equals 200. And we can now divide both sides by 2, so let's do that. Y squared equals 100. And let's take the square root of both sides to get us y by itself. And we see that y equals 10 because it has to be positive because it's perimeter. Now that we have our y value, we can solve for x. If you remember, our area equation is 100 equals x times y. And now we see that x equals 10 also. Now that we have both x and y, we can go back to our p of xy equation and substitute these values in. So we get 2 times 10 plus 2 times 10. So we now see that the perimeter is 40. Now let's think about the problem we just solved to modify our new problem. So now, instead of fencing in a real-life example, we are minimizing a value on a circle. Let's read the new problem. Find the minimum value of x squared plus y squared for all points x, y on the line 2x plus y equals 1. How can we adapt the fencing problem to a problem like this? Let's start with identifying our two functions. In our fencing problem, we wanted to minimize perimeter, so that was our objective function. The area was used to constrain the perimeter, so that was our constraint. Pause the video here and see if you can determine which function is the objective function and which one is our constraint. Okay, now let's see how your answer compares with mine. The first equation of the circle x squared plus y squared is what we want to minimize for all values of x and y. So our objective function is x squared plus y squared equals, let's just call it z of xy. So the line 2x plus y equals 1 limits our values of x and y, so that will be our constraint equation. Now that we have our two functions identified, we can begin to solve the problem the same way we started our fencing problem. Let's take our constraint equation, 2x plus y equals 1. we can either solve for x or y, so let's pick y because it will be easier. Now let's subtract 2x from both sides. So we get y equals 1 minus 2x. We will now take this y and substitute it into our objective function. Our original objective function is x squared plus y squared equals z of xy. Now let's rewrite our objective function with the y we just solved for in the last slide. Our equation is now in terms of x, so we can write x squared plus 1 minus 2x squared, gotten from the constraint, equals z of, now it's just x. Let's FOIL 1 minus 2x quantity squared using the Wolfram Alpha FOIL calculator. So let's type in parenthesis 1 minus 2x parenthesis caret squared and hit calculate. So we see that 4x squared minus 4x plus 1 is the result of that foiling. Rewriting what we got from Wolfram Alpha, we have 4x squared minus 4x plus 1. But we can't forget about the other part of z of x. So we can write z of x again as x squared from the first part plus the quantity 4x squared minus 4x plus 1. Combining like terms, we get z of x to be 5x squared minus 4x plus 1. So now that we have z of x, what do we do now? If you remember from the fencing problem, our next step is to take the derivative of z of x. Let's again return to Wolfram Alpha to derive this equation. If you want to take the derivative by hand, skip ahead one slide in this video. Now that we're on the Wolfram Alpha derivative calculator, let's type in the box 5x squared minus 4x plus 1. And we're taking the first derivative, so this will work. So hit calculate. So we see that 10x minus 4 is the first derivative for z of x. Since we know z of x is just a value for x and will be a constant, we know when taking the derivative z prime of x will be 0. So let's rewrite this as 0 equals 10x minus 4. Now let's go ahead and solve for x, so we get 4 equals 10x. Divide both sides by 10. We get x equals 4/10, which can be reduced even further to 2/5. Now we can solve for y. Let's go back to our constraint equation, y equals 1 minus 2x. Now we know x is 2/5, so let's substitute that in for x. So we get y equals 1 minus 2 times 2/5. If we multiply across, we get y equals 1 minus 4/5, which is just y equals 1/5. Finally, we can write our point x comma y as 2/5 comma 1/5. So 2/5, 1/5 is the minimum value of x comma y. For this minimization problem, we first found our objective function and our constraint. We solved for y with our constraint. Then we made a new objective function in terms of just x. We took its derivative and set it equal to 0. We solved for x and then y. And then finally, we found our minimum values for the point x comma y. Here is a more challenging problem for you to practice minimization with. A cylinder-shaped can holds 4,000 cubed centimeters of water. Find the dimensions that will minimize the cost of metal when making the can. Now you will have to look up the equations for volume and surface area of a cylinder, and you will solve it similarly to the ones we just did. Good luck! Thanks for watching.